In the previous two videos that you've watched, the first one, Boyle's Law, stated a mathematical relationship between volume and pressure. In order for Boyle's Law to be true, however, you had to have a fixed mass of gas and you had to hold that gas at a constant temperature. Well, the next one, Charles' Law, was a mathematical expression of the relationship between volume and temperature. Again, you had to hold the mass of the gas constant, but for Charles' Law to be true, you had to have a constant pressure. Well, what do you do in circumstances when both the temperature and the pressure are varying simultaneously? When that occurs, you use what is known as the combined gas law. The combined gas law, sometimes known as Boyle's and Charles' laws combined, is just that, a mathematical result of combining Boyle's law of V1 P1 equals V2 P2 with Charles' law of V1 over T1 equals V2 over T2. And I think if you look over here on the right, you can see that that's exactly what has happened. We have combined those two previous laws into one mathematical expression. Before attempting to solve any problems utilizing the combined gas law, I need to introduce you to the idea of standard temperature and pressure. As you know, temperature and pressure vary from location to location, and furthermore, gases are highly sensitive to changes in temperature and pressure. And so when we compare two gases with each other, we want to make sure that we are comparing them under the same set of conditions. And these conditions are known as standard temperature and pressure. And for gases, standard temperature is 273 Kelvin, which would also be 0 degrees Celsius, and 1 atmosphere of pressure, or its equivalent. Okay, and that could be either 760 millimeters of mercury or 101.325 kilopascals as well. So if you encounter the terms standard temperature and pressure in these problems, as you will very shortly, that's what we're talking about. Here's combined gas law sample problem number 1. It reads as follows. The best corals are at a depth of approximately 10.0 meters. Suppose you decide to take a deep breath and dive to investigate them. At the surface, your lung volume is 2.4 liters, the air temperature is 32 degrees Celsius, and the pressure is 101.3 kilopascals. At 10.0 meters, the temperature is 21 degrees Celsius, and the pressure is 141.2 kilopascals. What is your lung volume at 10.0 meters? Okay, a lot of information given here. Let's slow down, take the time to work through it and identify each variables. At the surface, your lung volume is 2.4 liters. 2.4 liters, that's going to be V1. The air temperature is 32 degrees Celsius. Okay, that's our first temperature. That's T1. Now, bear in mind that before we can use that temperature, we're going to have to convert it to Kelvin, but nonetheless, that is T1. And we're told that our first pressure, our initial pressure, is 101.3 kilopascals. That's P1. And you probably recognize that as an abbreviated form of standard atmospheric pressure. Okay, once we've gone down to 10.0 meters deep in the water, the temperature is now 21 degrees Celsius. That's our second temperature, so that's T2. And the pressure, because of the effect of water at depth, is now up to 141.2 kilopascals, and that's going to be P2. What's your lung volume at 10.0 meters? Lung volume. So volume is what we're looking for. We're looking for V2. So what I've done here is identify 5 of the 6 variables that make up the combined gas law. Well, let's start plugging them in and see what we can come up with. Okay, the revised version of the equation, okay, that we're going to use here is going to be V1 P1 times T2, all of that over T1 and P2, all of that equals V2. Now, if you don't know how I've gotten this from the regular form of the combined gas law, then you need to go back and work that out on your own. Okay? Before I can go any further, I'm going to make my temperature conversions. T1, which is given in the problem as 32 degrees Celsius, 32 degrees Celsius, I got to add 273 to that. So my real T1 that I can use in the problem as I solve it is going to be 305 Kelvin. Okay, that's T1. T2 is going to be 21 degrees Celsius plus 273, and that's going to be a temperature of 294 Kelvin. Okay, I'm ready to start my substitution. V1 is 2.4 liters. 2.4 liters. P1 is 101.3 kilopascals. And as always, notice I don't just substitute numbers, I include units. Numbers without units in a science setting mean nothing. T2, be careful, T2, not T1. T2 is 294 Kelvin. That takes care of my numerator. Now, denominator. Okay, T1, 305 Kelvin. P2, 141.2 kilopascals. And all of this is equal to V2. And when I do my calculator work, I come out with V2 equals 1.66 liters. And that's a volume, liters, because all my other units have canceled out. And it's already in scientific notation. That reflects 3 significant figures. So I'm done with this first combined gas law sample problem. Combined gas law sample problem number 2. When a helium balloon is fully inflated, it has a volume of 12.5 liters. When the volume of the balloon reaches 11.5 liters, the clerk filling the balloon stops to check the pressure. The pressure is 102 kilopascals and the temperature of the helium is 5 degrees Celsius. The clerk proceeds to fill the balloon to its final volume of 12.5 liters and observes that the pressure is now 105 kilopascals. When a customer takes the balloon outside, it explodes. What was the temperature outdoors in degrees Celsius? Okay. The first volume of importance is this one right here, 11.5 liters. Okay. That's V1. That's the volume at which the clerk stops the filling process to check temperature and pressure. And here's the first pressure. The clerk reads a pressure of 102 kilopascals. So P1. And the temperature of the helium is 5 degrees Celsius. There's T1, but as always, remember, we're working with gases. We're going to have to make the conversion to Kelvin. Okay, I've got V1, T1, and P1. The clerk proceeds to fill the balloon to its final volume. Final volume, 12.5 liters. So this is going to be V2. Okay, V2. The pressure in that balloon when it's filled is 105 kilopascals. Okay, so that's P2. We're being asked here, what's the temperature when this balloon is taken outdoors and explodes? So we're looking for T2. And furthermore, notice ultimately we want it in degrees Celsius. Before I bother to substitute anything into an equation, let's go ahead and make our temperature change. My initial temperature, T1, is given as 5 degrees Celsius. 5 degrees Celsius plus 273, and we get a Kelvin temperature of 278. We're ready to go now. The rearranged form of the equation is going to look like this. T2 is going to be equal to V2 P2 T1 over V1 P1. Time to start substituting. T2 is equal to the final volume, 12.5 liters. That's the final volume. Okay. P2, well, it's 105 kilopascals when the balloon is taken outside and explodes. And our initial temperature, we just made that conversion, it's 278 Kelvin. Be careful where you substitute your temperatures. That completes my numerator. Let's go to the denominator. The initial volume, when our conditions were first checked, 11.5 liters. And the initial pressure, 102 kilopascals. Time to get out our calculators, do a little plugging and chugging. T2 equals 311 Kelvin. Okay, when we solve the problem, we get a Kelvin temperature, but let's go back up here. We want that outdoor temperature in degrees Celsius. So we're going to take 311 Kelvin. We're going to subtract 273 from it, and that's going to give us a Celsius temperature of 38 degrees. And just so you know, human body temperature is about 37 degrees Celsius, so this is right around 100 degrees. So it's a rather warm day when this balloon ruptures under these circumstances. Here are your two combined gas law practice problems. One helpful hint for each. In number one, I'm looking for P1, initial pressure, P1. And in number two, you're looking for V1, the initial volume. Good luck.